Hasselman. There are two lectures organized by Divecha Centre for Climate Change, one by Professor J. Srinivasan and another one by Professor Ashwin Seshadri, about the work of Professor Manabe and Professor Hasselman. During early 1960s, Professor Manabe demonstrated how increases in carbon dioxide in the atmosphere can increase global temperature. This has provided a foundation and led to the development of climate models. Professor Hasselman developed a model that helped to explain how climate models can effectively be used even though the weather is chaotic in nature. He also explored the impact of human influence on climate. And the third winner who shared the prize, Professor Parisi, developed a model that made it possible to understand complex systems. So I request Professor Srinivasan and Dr. Seshadri to deliver the lectures. Thank you.
Thank you, Satish. I'll upload my presentation. Is it visible?
Yes, sir, it is.
Presentation? Okay, thank you. So good afternoon. So early this month, all of us were surprised when the Nobel Prize in Physics was given to two climate scientists for groundbreaking contribution to our understanding of complex systems, in which Earth climate is an example. Okay, and we are going to talk today only about two of these scientists or climate scientists. Giorgio Parisi looks at complex system, and he has done some work related to climate, which I hope Ashwin will touch upon. Yeah, I start with a quote from Gavin Schmidt, director of NASA. And I think all of you who work in the area will agree, climate science from its very beginning was wonderfully multidisciplinary endeavor, which has biology, chemistry, history, paleoclimate, and physics. Okay? And so all of us have been dealing with it for the last so many decades. But the topics beyond this are also key for understanding how Earth's climate and life evolved on Earth. And because of this multidisciplinarity of this field, Gavin Schmidt says he always assumed that climate science would never attract the attention of discipline-based Nobel Prize committees, mainly physics and chemistry. Okay, so we also thought that this would not be considered suitable for a Nobel Prize. Okay, so it's a surprise. Let's just briefly dwell upon the surprise. Now, when he heard the news, Professor Manabe, who is a very modest person, he said, "I never dreamed I would win the prize. If you look at the list of past winners, they are amazing people who have done marvelous work. In contrast, what I have been doing is trivial. But I'm not going to complain." Okay. Now, this attitude is understandable because let's look at the people who have won Nobel Prize in Physics in the last 100 years. We start with Einstein, who in 1921 got this for discovery of the law of photoelectric effect, not for relativity. And all of us know that he changed our understanding of the space-time relationship. And he started the whole area of cosmology. And he not only made this discovery, he also, of course, was one of the first people to see quantum effect. And so he's considered the greatest scientist of the 20th century. Okay, he's a different class, obviously. But remember that during this period, from 1921, most of the prizes are given to people in the area of quantum mechanics. But that was a field evolving rapidly at that time. And we know two more names, Erwin Schrödinger, who derived their equation, and Paul Dirac. Both these are absolutely great names. And they made big impact in quantum mechanics. Now this went on, and in 1928, the only Indian to get Nobel Prize working in India, Sir C.V. Raman, got it for Walker scattering, which is connected to the quantum nature of matter. So, so this went on for next almost 30, 40 years. Most of the prizes were for people who discovered something related to quantum mechanics or found new elements as the nuclear power was discovered. So nobody ever thought of looking at macroscopic physics coming from Newton's law as a place where you can do something new. But in 1978, there was a surprise. Penzias and Wilson got for the discovery of the cosmic background radiation, which is the radiation which is there from the Big Bang. And this was a big step forward. I must tell you why. Because when Srinivasan's nephew, H. Chandrasekhar, decided to work on astrophysics at the age of 20, Srinivasan discouraged him. He told him, no, that is not a great area. It's applied physics. And what can you find? I mean, because at that time, there were hardly any observations in cosmology which will help. But as you know, Chandrasekhar made some great discoveries, including the black hole, and he got rewarded much, much later. But Penzias and Wilson got it for showing that we are surrounded by uniform background radiation, which comes from the Big Bang. Now, a few years later, or 15 years ago, another two Nobel laureates got it for the same work, but this time discovering the anisotropy of the cosmic background radiation. And these are all great discoveries because they tell us about the origin of the universe, origin of this planet solar system. So these are absolutely mind-boggling work. But occasionally Nobel committees do unusual things. For example, in 2014, they gave 3 Japanese scientists for inventing the LED, the blue LED, because without blue LED, you will not get white light sources. This is many consider to be purely technology, not physics. But the Nobel Committee realized the importance of this work in society. So now and then, the Nobel Committee does go into areas where, like lasers and LEDs, where they think that discoveries have made impact in society. Now, 2 years back, 2 people got Nobel Prize, Mayer and Klaus, for discovering exoplanets. Okay, and it's very interesting that only 2 days back we heard that exoplanets was discovered in another galaxy, not our own galaxy. So this is all very unusual developments in cosmology and astronomy. Now, about 26 years ago, Nobel Prize in Chemistry was given to 3 scientists for understanding how ozone is depleted. And I remember that when this prize was given, this area of environment really, when the prize was given, a lot of chemists during doing pure chemistry were very upset. They were saying that, we all look at the chemical reaction at the molecular scale and do very sophisticated work. And why give prize to these 3 guys who merely looked at few reactions and how that reaction causes ozone to deplete? But I think they missed the main point. Although pure chemistry and pure physics is very important, now and then applied physics, applied chemistry also is very important to us because it affects our life. Remember that these 3 scientists warned us about the ozone depletion, and their warning was ignored for about almost 15 years. And once the ozone hole developed, people woke up, and that's when the Nobel Committee felt that they have to be rewarded for warning the world. So this year, I think the situation is similar. Many people have been talking about global warming for the last 100 years, but most of them are not taken seriously. But now this year, with the after the Paris meeting, there's another meeting starting on 31st of October in Glasgow, the COP26 Committee of Parties. And the nations of the world have to make tough decisions to decide how to control the Earth's climate, which is rapidly warming. So they thought this is an appropriate occasion to reward people who worked on this complex problem, although it did not involve any fundamental discovery. So Nobel Committee said it realized the understanding and predicting the Earth's climate is important. Now, this is as important as understanding the origin of the universe and other things, because if we do not understand our Earth system and its climate, we may very soon be extinct. So that's a fundamental question of survival. Now, the person who got the award, one of the persons is Professor Manabe. He was born in 1931. He is 91 right now, in a small village in Eime Prefecture in Japan. And he belonged to a family of doctors. His father was a doctor, his doctors. So all of them expected him to study medicine. But Manabe had interest in maths. So when he went to college, he switched over to maths and physics. But I must also tell you that Manabe mentioned that when he was in his teens, it was a very difficult period. Japan was at war, and there were frequent bombings, and food was not available. So he has mentioned in an interview that he was highly malnutrition. He did not get enough food to eat. But still, because of his drive, he managed to study for his entrance exam, similar to JEE in India, and joined the University of University of Tokyo. So he continued to work on geophysics. He got his doctorate there. And the interesting point he has mentioned in his oral history that he did not get along with his doctoral thesis advisor, because his advisor was very much involved in mathematics alone. Can you mute?
Professor Balaji, could you please mute your mic? Professor Balaji, can I have your attention, please? Thank you.
Yeah, can you hear me?
Yes, sir.
Yeah. So Professor Manabe didn't get along too well with his doctoral advisor because he had different views. But fortunately, his advisor allowed him to do his own work. So he managed to do his PhD with his own interests. And his interest at that time was in forecasting. And the work he did and he published was recognized in United States. People read his papers and thought that this was a very bright young person. So he joined the US Weather Bureau in the 1950s to work on the three-dimensional models of the atmosphere. Okay, the person who employed him was a great person, Joseph Pergonsky, who is the person who started the Geophysical Fluid Laboratory in Princeton, New Jersey. And it started as a US Weather Bureau, and he was a founding director. And he had an amazing knack of identifying promising young people. So based on the paper written by Manabe, Syukuro Manabe, he invited him and two other Japanese scientists. Now, all of you must remember that this was the 50s, just after the Second World War, where there was fairly strong anti-Japanese feeling on account of Pearl Harbor. But still, it goes to the credit of Joseph Pergonsky that he decided that you'll attract the best minds to his laboratory, and he went out of the way to ensure that they got their visas and ability to settle down in USA. So this is one of the interesting things about America, that most of the Nobel laureates are people who migrated from other countries because America offered them certain opportunities which was not there in their own country. So, the main work was started here, but it was remember that Syukuro Manabe was also a little lucky that at that time, America was the world leader in computers. And that is because of another genius, von Neumann. All of you know about him. So he had already started, after the Second World War, making sure that United States was a leader in computing. And he was convinced that computing will play a major role both in weather forecasting and in climate modeling. That was the genius of John von Neumann. So at his instigation, this Weather Bureau created this General Circular Research section in which Manabe joined. And this is a computer based on walls, which was there in 1940s and 50s. And so I must tell you that when I talk about the work of Manabe, all of you must remember that the computers he used for modeling were very primitive. I want to remind you that the computers used, let me just get the pointer going. Yeah, the computers used were about 10 to the power 10 times slower than what we have today. Okay, and to make it even clearer, most of the computers used at that time were slower than the power you have in your own mobile. Okay? So he had to be very clever in his work because he could not do anything very complicated that all of us can do today. And this is what I want students to appreciate. If you listen to my talk, you will wonder, why did he do such simple things? That's because he could not do very complicated things. Okay? This is Manabe with Spagansky in the lab talking about weather forecasting. He soon moved over to a longer time scale integration of atmospheric models. Now, you must remember that before Manabe's contribution, others had also done some work to understand the role of carbon dioxide in Earth's climate. It goes back to Fourier and then Arrhenius and engineer called Callendar. But you must remember that all these people worked in the pre-computer era. Most of the work was a zero-dimension model, and it did not account for variation pressure from surface to the top of the atmosphere, which is very critical for radiation heat transfer because the pressure broadening changes a lot between surface and, let's say, 10 kilometers. But still, these people had a clear inkling that carbon dioxide will change climate. But Arrhenius' interest was mainly in the past climate. He wanted to know how the ice ages ended. Now, Callendar was an engineer who worked in steam power plants, amazing person who figured out how carbon dioxide affects Earth's climate. But he argued that this will be beneficial to human beings, not bad. So 1930s, he wrote a work in which he said, this will be good for us because all the cold countries of Europe will benefit with the warming by CO2. Now, Manabe, his first work was in 1961. This was a model with only one dimension. From zero dimension, we moved now to one dimension because computers became available. And this one dimension was vertical. And he showed how the temperature profile in the vertical atmosphere due to radiation becomes adjusted with convection. Now, this is something nobody else had earlier looked at. And as a matter of fact, many people criticized him because he ran the model with only radiation. And once radiation created a temperature gradient near the ground, which was very steep, he decided that it is unstable and he adjusted it to a value of 6.5 Kelvin per kilometer. This is empirical. Now, a lot of people said that's not right. You should actually get the model to have a circulation, and that circulation might determine the lapse rate. That is right, of course. But remember, this is 1961. He did not have access to a very fast computer, and he could not run a 2- or 3-dimensional model. But he had a very good intuition. And with this model, he was able to get results which are pretty much as good as what we have today. So this is a result. You can see that initially the model will produce this red line, which is the radiative equilibrium, pure radiation, no fluid motion. And then he will, first thing they did was adjust the dry adiabatic lapse rate, which is 9.8. But then because there's moisture in the atmosphere, we have to come closer to moisture adiabatic. And the observed value at that time was around 6.5. So he adjusted it to 6.5, almost up to tropopause. And beyond that, of course, ozone warming took over, and we had a stable lapse rate here. So this is the first work, which is very highly cited work, which all of us use in our courses. Now, this is cited in the Nobel Prize website, saying that it's the first climate model which used radiation to create the temperature gradient and then adjusted it to take care of convection. So this was the first model that did that and got fairly reasonable answers. Now, the second thing is a major contribution is that when he ran the model and increased CO2 from 150 to 600, 150 corresponds to somewhat closer to the last ice age, 300 to somewhat close to pre-industrial, and 600 was supposed to be the future. And what Manabe noticed was striking. He saw that the temperature went up in the troposphere, but it decreased in the stratosphere. This was the first time it was clearly shown that due to increase in greenhouse gases like carbon dioxide, Earth's troposphere warms and stratosphere cools. Now, this is a very counterintuitive result. Many people didn't believe it. But today, anybody who reads a textbook in climate science radiation will know that the reason why stratosphere cools because of the positive lapse rate. Because the temperature at the higher level is more than lower level, if you increase carbon dioxide, it loses more heat at the top than it gains on the bottom. So it cools. But this was his first discovery, and this was just done by a one-dimensional model and by an empirical adjustment of the lapse rate, which a lot of people didn't like. Now, this fact that CO2 causes cooling in the stratosphere and warming in the troposphere was immediately, immediate impact of that was seen by Hasselmann, the other Nobel Prize winner this year, and he saw this as a spatial fingerprint. Now, this is very important because in 1979, people didn't believe that CO2 will cause global warming. And they said it could be due to change in sun's radiation, maybe some other factor. Now, if sun's radiation was causing warming, it will warm both the troposphere and the stratosphere. The fact that troposphere was warming and stratosphere cooling in the observations, one can be quite sure that the fingerprint of CO2 increase is seen clearly. That was the point he made, that this can be used to detect greenhouse gas single in observation, and Ashwin will talk more about this fingerprint approach. Now, Manabe also showed how the different gases contribute to warming and cooling of the Earth's troposphere and stratosphere. Each of the gases he identified, ozone, carbon dioxide, water vapor. This is the solar side, this is the long wave side, and put all together, they show clearly that the radiative convective equilibrium prevails over the troposphere and radiative equilibrium occurs in the stratosphere. So this is a repeat of this from one of the papers of Manabe. Now, the next important work that Manabe did was related to the role of water vapor. Now, before this, although people like Callender had suggested water vapor plays a role, but again, it was not taken seriously. And water vapor plays a very fundamental role in Earth's atmosphere. It's very complex because water vapor has three roles in the Earth's climate. One, because it's a very powerful greenhouse gas, more powerful than CO2. Second, because it is lighter than air. Its molecular weight is 18, air is 29. When water vapor appears in air, it changes the buoyancy of the air. Okay? So that is a very important factor in convection. And thirdly, water vapor, when it condenses, it releases a huge amount of heat. So water vapor plays three different roles in the Earth's climate, and without modeling, you cannot decipher the three roles it plays. It's very complicated. So in a model, you can stop one and not the other and see what happens. So this was the first work by Manabe and Vedder, which is highly cited because they were able to show, and they assumed a known profile of humidity in the atmosphere, which was measured in some places. And Manabe, Spragansky, and Strickler published the first paper on thermal equilibrium with constant relative humidity. Again, this was the original idea of Manabe, that you cannot keep specific humidity constant, you have to keep relative humidity constant. That was, again, an original idea, which many people didn't believe, but we know now that that's a very good assumption. Now, then Manabe went on. He was not satisfied with purely atmospheric GCM because he felt that ultimately ocean covers most of the Earth and the Earth's climate is controlled by the ocean. So the first model he developed with Kirk Bryan, who was an ocean modeler. So in 1969, he developed the first coupled model, coupling between atmosphere and ocean. And the first ocean he developed was called mixed air ocean. That is, ocean had no convection, no circulation. It was just a pond containing a lot of water, and it exchanged energy and water vapor with the atmosphere. So this model itself gave a lot of interesting results, but he moved on to include sea ice and show the effect of ice and so on. But finally, he went on to a full coupled model, which included circulation in the ocean also through conservation of momentum, mass, salt, energy, and the equation state for the ocean. So now we had a atmospheric model and an ocean model, both containing all known laws of macroscopic physics. Now, the problem with this coupled model, which was run for the first time in GFDL, is that it would not reach a steady state. Because remember, if you run the model for a long period, ultimately the atmosphere and the ocean must come to some kind of equilibrium in the exchange of momentum, mass, salt, heat, and everything. But it did not. It won't reach steady state. And he realized that it is because there were some errors in the way energy and mass were being transferred between the two medium. Okay, because atmosphere has a very short response time, and the ocean has a very long response time. So there is a problem. So he took a shortcut. He did what we call flux adjustment. So he wanted the system to reach steady state after long integration. So he had to adjust the flux. A lot of people didn't like it because it is arbitrary, it is ad hoc. But remember that he was doing work at a time to integrate this coupled model for 1 year. It took 1 year of computer time. So he couldn't afford to try to improve the model and try to get rid of this bias in the model. He had to quickly fix it. So it took a what I call an engineering approach and made empirical adjustment. Today, we don't do that. Today, the models have advanced so much and the computers become so rapid that we are able to do a more accurate interaction between ocean and atmosphere. But at that time, 1960s, they had to do flux adjustment. There was no alternative. So this is the model they had, in which you had equation for the atmosphere, fluid mechanics of the atmosphere, and then water, salt, all the budgets in the ocean, and the two interacted together. Okay? So I must tell you that this coupled model is the forerunner of all the models used today. As a matter of fact, the ocean model developed in GFTL is used almost in all the models in the world. It is called the modular ocean model, MOM. And today you look at many models, including the one we use in India now. MOM is used as the main one. So this has contributed to development of models all over the world. The second thing I must tell you, because this work was done about almost 45 years ago, they had a very simple land-ocean configuration, okay? They did not allow things to vary a lot with that longitude. They specified the fraction of land at various latitudes. That's all they could do. And the model resolution was quite crude, 500 kilometers. So something today we will not accept, but at that time, that was what was possible. Now, this is the important result they got from this coupled model. They ran the coupled model for 500 years, which was a challenge those days. And they showed that in the model, if they fixed water vapor and doubled CO2, the warming was only 1 degree. But if they allowed water vapor to vary as per the laws of thermodynamics, the warming was 3 degrees. This was the first demonstration in a complex model of the feedback due to water vapor. So what they showed so nicely was that if you double CO2, the Earth will warm only by 1 degree, and it is because of water vapor increase and the greenhouse effect of water vapor and melting of ice that additional 2 degree warming occurs. So I must tell you that today we have about 1.3 degree warming since 1850, but all the 1.3 is not due to CO2. CO2, you can say, contributes to around maybe 0.7, 0.8 degree. And then we have about 1.4, 1.5 due to water vapor. But actually, if you include only water vapor and CO2, the temperature today should have been 1.8 degree. It is not 1.8 because when we burn coal, oil, you also release sulfur dioxide gas, which becomes sulfate aerosol, which cools the earth. So we are somewhat lucky that this pollutant sulfur dioxide has prevented the warming from going up more rapidly. Okay, so this was the first demonstrated what called feedback, and this was not recognized earlier. As a matter of fact, all of you must have heard of Milankovitch, a famous astronomer, who had a theory for ice ages. His theory was completely ignored by most people because at that time, this is 1920s, feedback was not known. Feedback was not understood, especially the water vapor feedback was not understood. So Milankovitch died without realizing that the model he had proposed for the Earth's ice ages was correct. He did not was not able to see the results we see today. Now, Manabe just didn't do global warming and CO2. He was very much interested in what happens in the past climate. So he simulated this coupled model, and ice sheet also was brought in, and then it showed clearly how much role the ice sheet played in the cooling during the last ice age, how much role CO2 played, how much role the land reflectivity change, albedo change played, and how the combined value was around 1.9, and proxy evidence shows 1.6, which is quite good in this comparison, because proxy evidence is not perfect. So Manabe was also able to throw light on the past climate. Not only future, but past climate. That was his contribution. Now, you must remember that when he ran those models, which are not very high resolution, there were problems. For example, he showed on one of his papers that his model would not get the Antarctic temperature correction. The crosses are the observation and solid is the computation. You can see there is error almost 20 degrees in Antarctica because ice sheet, other things are not properly modeled. But he showed that although that error was there, if you look at the change in sea surface temperature between present climate and last ice age, the difference, the model reproduced the proxy observations, which is called CliMap. So the model was quite good in spite of some errors in the Antarctic region. Now, these models he used were very, very simple. For example, his land-ocean configuration is symmetric. He had three little strips of land, 3 strips of ocean. Many of you may laugh at it now because that's what he could do, because he had to use fairly a low-resolution model. He couldn't get the exact configuration of the oceans. If he did that, it would take too much effort. So by these simple models, he was able to get results to understand how the Earth's climate changed. Today, we are living in an era where we run very complex models. So when Manabe started, we are in the left corner here, atmosphere, land, and ocean. And in the 70s, slowly, Manabe also added sea ice and uncoupling. And later on, people added aerosols, and aerosols are recognized important. Then they added carbon cycle and vegetation. Then now people are adding dust, sea spray, interactive vegetation to understand past climate, and biogeochemicals in the ocean. So the models are getting very complicated today because the computing power we have is 10 to the power of 10 times what Manabe was able to get. So we have reached very far from where Manabe started, but you must remember it was Manabe's very original thinking in the 60s and 70s, which has led this direction. And GFDL, where he worked, was really the place where people were trained and people went from there to Australia, to Japan, and everywhere in the world. Okay? Now, I must also mention that because of the work done by Manabe and many other people over the last 50 years, today we can, our uncertainty about the climate models is around 20%. If you look at our prediction for 2100. The major uncertainty today is not the model, but scenario. That is what we human beings will do to the climate because how we release the amount of CO2, what we do about controlling our carbon emissions. That is the major uncertainty, not the model. So to that, we have to give tribute to people like Manabe and his other people who followed up. And I want to end my presentation by pointing out, Manabe was asked, whenever people get Nobel Prize, the press gets a bit hero worshipping type, and they say, what will be your advice to people attending the COP26 next week? Manabe, being a very modest person, said, hello? Can you hear me?
Yes, sir, we can now.
And somebody removed me. I think you have to find out. Somebody removed me from the meeting. So this has to be looked at how it's happening. Okay, can you see the slide?
Yes, sir.
Yeah.
Yes, sir.
So what I'm saying is that Manabe was asked a silly question, what will you advise COP26 leaders? He said, formulating a climate policy is 1,000 times more difficult than making climate predictions. So although the problem is complex, the problem of human beings trying to control carbon emission is even more complicated because it involves people and not just physics and chemistry models. And if any of you want to know more about the wonderful Manabe, he wrote a book a few years ago to simplify his science so that others can understand how numerical models reveal the secrets of climate change. And so all of you, I recommend you should read this book, very in simple language and good figures. And then he has said, prediction of climate change without accompanying understanding is no better than prediction of a fortune teller. So this is a very good remark. Today, because we have powerful computers and complex models, we can make predictions. But if we don't understand the prediction, we will be like an astrologer. So this is the point Manabe made in his life. He was driven by curiosity, and that alone enabled him to unravel the complex Earth system. And as we go forward and use more complicated computer models and artificial intelligence, machine learning, you have to remember that in addition to predicting, we have to understand what the model is doing. Otherwise, we'll be fortune tellers. Okay. And so the last quote is, I never imagined that this thing I would begin to study had such a huge consequence. He was not an environmental activist. I was doing it just because of my curiosity. So it shows you how far one can go if you are allowing yourself to be driven by curiosity. And Manabe is a wonderful example. So thank you. And I want now Ashwin to take over.
Thank you, Professor Jayes. I request Dr. Ashwin to share his slides and start the presentation.
Are my slides visible?
Yes.
Am I audible? Am I clear?
Yes.
Yeah.
Yes.
Okay. Hello, everyone. I'm going to briefly discuss the work of Professor Hasselmann, who shared one half of this year's Nobel Prize in Physics, equally with Professor Manabe. And as we shall see, and as Professor Jayes described, the later part of Hasselmann's work on fingerprinting of climate change rested on developments in the climate modeling that were made by and pioneered by Manabe and his colleagues. So here's a biography of Hasselmann from his website at Max Planck Institute for Meteorology. He was born in 1931. He trained in physics and mathematics. For his PhD, he worked on fluid mechanics, studying shock waves. Then he completed what's called a habilitation, also in physics. And following this, began a long career, first at Hamburg and then at Max Planck. So here are the papers of Hasselmann that have been mentioned by the Nobel Committee. Turns out an early focus was fluid mechanics, using methods of theoretical physics. And there was a fair amount of emphasis on geophysics, especially understanding interactions between waves. For instance, surface waves in the ocean generated by wind. But the prize award comes for work that was done after this and can be divided in two phases. So first in red, the papers in red, is the study of what are called stochastic climate models, which appeared in the journal Tellus. These are models where the weather component is treated as a stochastic influence on climate, giving rise to stochastic differential equations. We'll talk about these in a bit. And by studying these equations, Hasselmann basically was able to estimate the statistics of climate, given the interaction between weather and climate. And the second contribution, the papers in blue below, is what is called fingerprinting. So the first paper in this group appeared in 1979, and it motivated the overall approach. The 1993 paper describes the method. So if you're looking for a good introduction to the approach of optimal fingerprinting, I would begin with the 1993 paper. The basic idea is very simple. Just as we all have unique fingerprints, different climate forces have their own fingerprint on the observational record, as Professor J.S. described. And Hasselmann developed an approach to optimally identify these fingerprints using statistics. So here's the first paper, the abstract of the first paper on stochastic climate models. Let me quote from the abstract. A stochastic model of climate variability is considered in which slow changes of climate are explained as the integral response to continuous random excitation by short period weather disturbances. The coupled system is divided into a rapidly varying weather system and a slowly responding climate system. Right? So there's a distinction between weather and climate. Weather is fast, climate is slow. Climate is modeled as depending on the cumulative effects of weather, and weather is a stochastic input, right, or random input to the climate. This gives a stochastic differential equation for climate that we'll see in a moment. And through this, he was able to use tools that were being developed elsewhere in the context of problems such as Brownian motion. In this way, he could relate weather and climate timescales. He was also able to shed light on the problem of climate predictability in the context of chaotic weather. So in his model, Hasselmann makes the distinction between weather and climate. Here's an illustration of these two different concepts. We associate weather typically with weather events, and the picture on the left is a particularly dramatic example of flooding in Honduras from a hurricane that happened last year. But a more general difference between weather and climate is of timescales. So here are two diagrams from Hasselmann's paper with a colleague. The middle panel shows the power spectrum of wind. Okay, wind velocity from a simple atmospheric model. Power is highest at time periods of about a week. Okay, and as you go further to the left, corresponding to lower frequencies, the power rapidly decreases. Right? This is fed into a model of the upper ocean. The spectrum of SST, that sea surface temperature on the right, is very different from the weather spectrum we saw earlier. It has more power at lower frequencies. So in summary, one major difference between weather and climate, and also specifically to Hasselmann's thinking about stochastic climate models, is in the power spectra of weather time series versus climate time series. Weather time series have longer frequencies, climate time series have more power at shorter frequencies. Longer frequencies, weather time series have more power at shorter time scales corresponding to higher frequencies. There's another difference between weather and climate. Forecasting weather depends on knowing the initial conditions, and this is closely related to the concept of chaos. Edward Lorenz was a mathematician who worked in meteorology, and this paper of his helped us understand chaos in the atmosphere. So chaos arises from repeated stretching and folding of trajectories in phase space, and these are shown in the diagrams on the left, and this happens in a very complicated manner. It gives rise to chaos. It's also known as sensitive dependence on initial conditions. So let's define a couple of terms that are relevant to understanding Lorenz's paper from 1963. A stable trajectory is one where nearby trajectories remain nearby for all times. A non-periodic trajectory is neither periodic nor what is called quasi-periodic. And Lorenz basically showed in this paper, it's called deterministic non-periodic flow. And here's an example on the top right. You have two nearby trajectories that diverge from each other in phase space after a certain amount of time. And this is exactly an example of what he's talking about. Lorenz showed that non-periodic trajectories are unstable. So this is a non-periodic trajectory, and Lorenz showed that this has to be unstable. Such trajectories, which are neither stable nor quasi-periodic, but nonetheless bounded, right? The system doesn't blow up or go to infinity. Energy is bounded, but it's neither periodic nor quasi-periodic. Such trajectories have to be unstable. What does that mean? It means the distance between nearby initial conditions must grow. And this is really the central challenge for weather prediction, right? The impossibility of measuring this is a quote from Lorenz, in view of the impossibility of measuring initial conditions precisely and distinguishing between, don't have to worry about what central means, between a central trajectory and nearby non-central trajectory. All non-periodic trajectories are effectively unstable, right? The heart of the matter is all non-periodic trajectories are unstable from the point of view of practical prediction. So there are many examples of this phenomenon. Chaos. This slide shows some other examples. The top left is the equations in a model introduced by Lorenz in his 63 chaos paper. It has 3 equations. One is linear, 2 are nonlinear. It's the first demonstration of chaos in such a simple 3D model. 20 years later, Lorenz introduced a model of mid-latitude circulation in 1984. And this describes the interaction between the mean flow and eddies. And this is also chaotic. And both of these models are 3-dimensional. They have 3 equations, and this is not a coincidence. Over 100 years ago, Henry Poincaré and Ivar Bendixson had shown that you cannot get chaos in 2 dimensions. Chaos, in other words, requires 3 dimensions. So I should point out, for understanding the historical record, in an important sense, chaos was discovered much earlier in the 1800s. So Hadamard introduced a point sliding on a 2D surface, the figure on the top right, a 2-hole donut, which was later shown to be chaotic. This is essentially a geometric problem. Poincaré introduced an approach to study the restricted 3-body problem, the 3 bodies in a plane interacting to the force of gravity, and this was also later shown to be chaotic. But this was actually the first known example of chaos. When first introduced, these models all gave rise to irregular trajectories from deterministic laws, and they formally are now known to be chaotic, even though at that time the language and concept of chaos as we now understand it was not appreciated. All right, but it was known that all of these systems give rise to irregular behavior well back in the 1890s. And what's common to all of them? They all give rise to irregular trajectories, albeit they arise from deterministic laws. So the appearance of randomness can arise via deterministic laws, and here are some everyday examples. You know, for example, coin tossing is an everyday example. You throw a coin up with a known velocity, a definite spin. You know when the coin will fall back down. And in principle, you can calculate heads or tails, assuming that the coin doesn't bounce. There are only 2 parameters to this problem, as shown in the figure here. One is u, it's the initial upward velocity, and one is omega, the spin rate. And depending on the combination, if you know u and omega, and especially u in relation to g, you will know whether you land heads or tails. Right? What the lines do is they distinguish regimes with heads and tails. But the challenge is that as either u or omega or both gets larger, especially if both get larger, these regimes get closer and closer, and practical prediction becomes impossible, right? So the regimes with heads and tails get so close that if there's any uncertainty in initial conditions, you're not going to know whether you're going to be in heads or a nearby tails regime. And so we cannot predict the outcome of an individual coin toss. But if we were to toss many coins, we know the probability of heads and tails. Another example is that of a pinball machine, and there's a very nice discussion of this in Lorenz's book, The Essence of Chaos. You strike a ball upwards from the bottom right. The ball ends up here. It strikes the pins and ends up somewhere at the bottom. Okay, you assume that the bottom surface is sticky enough that once it touches the bottom, it doesn't slip or slide or roll. Okay, but you might have 2 strikes with very closely spaced initial conditions, and the balls diverge. The balls eventually diverge. But you do this for many balls, and you know their eventual distribution. And this is also very closely related to the example on the right. It's a device developed by Francis Galton on the right to illustrate the central limit theorem. The idea is you drop marbles or beans from the top, and they make a bell curve. You may not know where an individual marble or bean may end up, but you know the statistics. So in each of these cases, we have deterministic laws. Individual realizations give the appearance of irregularity. some might even say random. Any particular realization is unpredictable, but the distribution is known. And Hasselmann used just such an idea in his work on stochastic climate models. So consider this is a simpler rendition of his work by the Nobel Committee, which I borrowed for the purposes of this talk, but it largely describes the spirit in which the first paper on stochastic climate models was written. So consider the evolution of two sets of variables. X is weather, Y is climate. We know that weather is fast, climate is slow. Weather is chaotic, as we saw. And the question he asked is, what does this mean for climate? And here's the basic idea. He expanded the equation for X, weather, in terms of the conditional expectation of Y, or of X given Y, as you would do in regression. It's the mean of X given Y, plus the residual X star. Some people also call it the anomaly. And that's simply, X star is simply the weather fluctuation. Then he substituted this expansion for X into the equation for the evolution of Y. Okay, the Y dot equals G of X comma Y equation. And then use the Taylor expansion. So the expansion of X is substituted into the equation for G. And so the rate of change of climate then has two contributions. The first term comes from the average weather given the climate, that is given Y, what's the expected weather? And the second term comes from the anomaly or the fluctuation X star. Okay. The first term depends only on Y, so is a function of Y alone. The second term comes from the weather fluctuation and is stochastic. Why is it stochastic? We saw earlier that weather fluctuates on shorter timescales. So this week's wind anomaly might be correlated with next week's, but not with the anomaly 1 year later. So on climate timescales, Hasselmann approximated X star as white noise. And this is one of the key innovations in his work. Then the climate model is a type of stochastic differential equation. It's called Langevin equation. There's a deterministic part on the top right, the minus lambda y. There's a stochastic part, the second part of the equation. And these kinds of equations originate in ideas of modeling diffusion, such as Brownian motion, and he could employ a very rich toolkit that existed at that time for analyzing such systems. For example, one can estimate the probability distribution of the climate variable, one can estimate its power spectrum. Most significantly, for our purposes, he showed that an input weather spectrum that is concentrated in high frequencies at the bottom, f of omega, where most of the energy lies in high frequencies, gives rise to a climate spectrum that is concentrated in low frequencies. You could study this theoretically as well as empirically. And such power spectra closely resemble the spectra of climatic variables that are observed in nature, such as sea surface temperature. And so this model generates spectra with more power in low frequencies because of the inverse dependence on omega square, as you see in this equation. Omega square is basically frequency squared. What is lambda? Lambda is the stabilizing feedback. Okay, this comes from the tendency of the climate system to restore equilibrium, as can be determined from an energy balance model, for example. So if lambda were 0, the energy in the low frequencies would grow without bound. In the presence of a stabilizing feedback, the low frequencies, that is frequencies with omega approaching 0, as you approach the origin in this curve, have finite power because of the dissipation induced by lambda. So what does lambda do? Very simply put, lambda brings the system back to equilibrium, and it limits the energy contained in the very low frequencies. And I cannot overemphasize how important this result is to understand a wide range of phenomena related to climate prediction. Okay? Not only in the stationary context, but also in the non-stationary context. All right, let's turn to the problem of global warming. Here's a key result in climate science named after Charles Keeling, who was a geochemist who began the first measurements of atmospheric CO2 in Hawaii in the 1950s. We see two things. We see a seasonal cycle. We also see a continued rise in concentration through the decades, and that's one of the more striking features of this graph. So this increase in atmospheric CO2 is directly related to global warming, seen here from the recent IPCC report. The black curve is the instrumental record, and it has been compared with the model simulations, with and without human forcing. The green curve is with only natural forcing, and the brown curve is with human and natural forcing. So just some reminders of some history, and I'm reiterating much of what Professor Jay has said. Of the history that brought us here, there's the early study by Fourier of the greenhouse effect, a calculation in 1896 of the potential magnitude of the CO2 greenhouse effect, and its increase through the burning of fossil fuels, to 1938, which is a very interesting year when Callender observed, based on temperature measurements until then, that the climate had been warming in the past few decades, and he attributed this to CO2. This is the first recorded statement, assertion of anthropogenic global warming, not the possibility of future warming, but the fact that warming has already happened and is evident in the instrumental record. It turned out that this was premature, as we shall see. And you can also see other developments here, such as a computer model of the global atmosphere, the first detailed calculations of the radiative effects, the finding that CO2 will not be readily absorbed by the oceans, calculations of the water vapor feedback. And all of these culminated in and enabled Manabe and his colleagues to make their first detailed calculations in the 1970s. Just a reminder of how we got here. Okay. But around this time, it turns out that the CO2 effect was noticeable, as seen in this diagram in a paper by Wallace Broker, published in 1975. The thin dashed line shows natural variability. The dots show the CO2 effect, which is increasing in time. The thick dashed line shows the sum, the total effect. And by the time this paper was published, the CO2-induced warming is comparable to the warming signal from the observational record. 1975, the vertical line. At the time of Broker, the CO2-induced warming is comparable to the warming from the observational record and much larger than internal climate variability. But at Callender's time, 40 years earlier, the warming signal was much smaller. And what he really picked up was the effects of natural variability. So even though by 1975, the CO2 effect was notable and significant compared to natural variability, the discussion about whether or not the greenhouse was upon us was continued well into the 1980s. Here's a quote from a report in Science magazine in 1988. The best bet for early detection seems to be the identification of a number of changes: warmer weather, warmer ocean water, a cooler stratosphere, and increased precipitation, for example, that together would in all likelihood be caused by a greenhouse. And why is this important? Because the view at that time was no one type of change is likely to convince the scientific community of the reality of the greenhouse effect until well into the next century, when the world would be condemned to dramatic changes. Okay. So these are early suggestions of the need for fingerprints. The quote on the right, the approach now being pursued is more like developing a composite picture of a culprit rather than arresting the first suspect who has the same color eyes. Researchers call the technique fingerprinting, although it is hardly as conclusive as the human technique. The human technique of fingerprinting on grounds of individuals' fingerprints. And one reason this debate carried on well into the 80s, despite what we saw about paper published by Broker in 1975, 13 years before, was because at that time most climate models did not render internal climate variability very convincingly. Right? They did not have dynamic oceans. So this was the early days of, the models in the 60s and 70s had thermodynamic ocean models. In the 80s, these were the early days of models having convincing dynamic oceans and representing natural variability adequately. So this is where Hasselmann's work. Okay, before that, these are some of the same fingerprints that we'll encounter and that Professor Jace has described. And as the report noted, fingerprinting was not conclusive, and there was really no objective method to identify what a fingerprint was. And this is where Hasselmann's work made a difference. In a series of 3 papers that we showed earlier, he showed how optimal fingerprinting could work. His 1979 article had set the stage. The abstract from it is at the top. The problem of identifying the mean atmospheric response to external forcing in the presence of natural variability of the atmosphere is treated as a pattern detection problem. It is shown that without the application of filtering techniques to reduce the number of degrees of freedom of the response pattern, the atmospheric response inferred from data or model experiments will normally fail a multivariate significance test. So the basic message is that filtering is crucial. One cannot expect statistical significance at every grid point due to effects of natural variability, internal variability in the climate system. In other words, the signal will most readily be apparent as a large-scale pattern. And the figure on the top right is actually the only figure in the paper. Its message is that the pattern that can most readily be found, the pattern that is the fingerprint of anthropogenic influence, this pattern might not correspond directly to the effect of the external forcing, because it will also depend on where the noise has the smallest variance. So noise here corresponds to natural variability, and the optimal signal to noise direction, indicated as B hat in this figure, would be some combination of strong signal and weak noise. It will not correspond to the direction of the strongest signal G if that direction also has large variance of noise, as shown by the end. So that's a very simple message of the paper after a fair amount of analysis. And remember, so at the time of this writing in 1979, the paper on the top, the scientific community had not yet begun to talk about fingerprints. But in light of the developments, the physical understanding of fingerprints of CO2 that Professor Jace discussed and the community's growing interest in identifying fingerprints, several climate scientists sought fingerprints, and in 1993, Hasselmann developed the insight that he had in 1979 into the first optimal fingerprinting paper. So I'm only going to mention this paper and perhaps read the abstract a bit and give you the main message. And the basic question is the following: how do you find the fingerprint? The answer is as follows. The optimal fingerprint depends on the signal pattern. It also depends on the inverse covariance matrix. So let's read the abstract. An optimal linear filter, a fingerprint is derived for the detection of a given time-dependent multivariate climate change signal in the presence of natural climate variability noise. Application of the fingerprint to observed or model-simulated climate data yields a climate change detection variable with maximal signal-to-noise ratio. The optimal fingerprint is given by the product of the assumed signal pattern and the inverse of the climate variability covariance matrix. Okay, so the fingerprint, we're not going to get into the mathematical developments, but the intuition is that the fingerprint is high, where either the signal is strong, for example, CO2 gives a strong warming signal in the Arctic, or where the effect of natural variability is small. In other words, the covariance is small. So if you're fingerprinting CO2, you're looking for a large CO2 effect or a small natural variability contribution. So there is a maximization of the signal to noise ratio here, and that's a direct line, but still a long line from the intuition of the 1979 paper to the methodology of the 93 optimal fingerprinting paper. And I'm not going to discuss the subsequent papers except to talk about applications. And all I will say is later this approach was extended to the multi-pattern case to account for different climate models, as well as greenhouse gases and aerosols. So it fell to his collaborators, Hasselmann's collaborators and others, to apply the fingerprinting approach to output from GCMs as well as identify fingerprints. And so here's a diagram from a more recent paper by one of his early collaborators, Gabriel Heger. The top panel shows warming between two periods in the instrumental temperature record. The middle panel is the optimal fingerprint of greenhouse gases and aerosol-induced warming in a set of 22 different models. I think these are the CMIP3 models. And the bottom panel is the difference. So what is this? What's the bottom panel? It's the best estimate of what part of the above change, the change in the top, the observed warming difference, comes from natural variability, and it's generally small. And the right panel shows the corresponding globally average time series. And the first thing you should notice is that the optimal fingerprint is clearly smoother than the global warming signal. And it's basically a filtered version. So there's a close relation between optimal fingerprinting and filtering along a direction where natural variability is small. All right, let me also show a figure from a recent article which appeared in 2019 to commemorate the 40th anniversary of three events that it noted as being very seminal in the field of climate science. One was a Charney report, which is in 1979, which estimated climate sensitivity to be very close to its present day estimate. The second was Hasselmann's article on optimal detection of high dimensional climate signals in the presence of noise, which provided the foundation for subsequent work on fingerprinting, as well as following it, detection and attribution of climate change. And so here's a figure from the paper. It shows the signal to noise ratio in detection of an anthropogenic effect in climate records. All these There are 3 different data sets. They all show a large signal to noise ratio at the 3 sigma threshold by the turn of the century. And this is, again, based on an application of Hasselmann's optimal fingerprinting approach. Now, I wasn't planning on, but since Professor J suggested it, I have included a slide describing a paper by Parisi. This is something some of you may have encountered. Parisi has written a couple of papers in the area of climate. This is about stochastic resonance and climate change. The context is there's paleoclimatic evidence of ice age cycles in the proxy record. Here's a power spectrum that motivates these are both figures from this paper. The power spectrum is one of the motivating figures in the paper. The idea is these ice age cycles have been observed to recur every 100,000 years or so. And this paper basically postulates a theory. And the theory is that of stochastic resonance. The idea is there's a slow oscillation in the basin of attraction. So these are the right-hand side shows potential wells describing the deterministic part. You can think of them as providing some basins of attraction, and there's a very slow oscillation. But it's well known in the paleoclimate community that this oscillation is too weak to by itself have caused transitions between glacials and interglacials. So the idea and the suggestion in this paper is that noise works in conjunction with this deterministic part. It resonates with this deterministic part to tip the system from one basin to the other. And that's the idea behind stochastic resonance. So there's a cooperation between the periodic forcing, periodic deterministic forcing that comes from orbital mechanics and orbital forcing of solar insolation on Earth and internal stochastic dynamics, stochastic mechanisms, which give rise to this periodicity in the glacial interglacial transition of roughly 100,000 years. So I'll stop here and thank you very much for your attention.
Thank you, Ashwin, for a nice summary of Hasselmann's work. Now we are open for questions. You can put the question in the question chat box or directly. Or you can put your hands up. Yeah, Vishal.
Yeah, thank you both of you for telling us about this year's Nobel Physics Prize. My question is to Ashwin. From your presentation, I got the feeling that Professor Hasselmann's methodology is applicable to the outcome of the models, or is it extendable to observations, either from satellites or ground-based observations?
The short answer is both. The short answer is both. So there are 2 parts of Hasselmann's work. I'm guessing you're asking about fingerprints, right?
Yes, yes.
Yeah. So the idea is, how do you compare models with observations? How do you look for fingerprints of what you expect forcing would do to the observational record? How do you learn how you would expect, what's your best estimate of what you'd expect a certain climate forcing, say CO2, would do in the observational record? For that, you use a model.
Mm-hmm.
Okay, so you use a model to derive your best estimate of what a forcing would do, that you can then seek in the observational record, that you can then map to the observational record. Okay, so you use observations, you use models to get a best estimate of a signal. You understand from the models the noise in the models, because that's also your best estimate of variability that fills space, that covers all grid points. And so you use the models to understand a couple of things. You use the model to understand what the expected signal is likely to be and what you can look for in the observational record. You use the model to understand internal variability as measured by its covariance matrix. Right?
Okay. Yeah. Yes.
And
that
together,
makes sense.
yeah, and together that will tell you what is your best direction in which you can look for effect in the observational record.
Okay. Yeah. Thank you.
Yeah, I should add that the Santa's paper is completely observational, right? That phi sigma he shows is completely based on satellite data.
That's completely based on satellite data.
Yeah.
Yes.
So Vishal, that's the point. It can be applied independently to observation and the model separately.
Okay. Yeah, that kind of is a clincher.
Yeah. And now Rohini had
Thanks.
put her hands up, but I don't see her there. Rohini, are you there?
Yes, sir. Thank you for this consolidated presentation. After seeing your slide on the evolution of the models, in fact, the evolution of details which go into building these models, how do we envisage in future how much more details, both, of course, practical measurements and climate modeling, would be warranted to study the warming of the Earth with respect to the continuous surge in greenhouse gases? So how do we envisage this in future?
Yeah, that's a good question, Rohini. Let me explain. Although models have become more and more sophisticated, they don't still predict how the glaciers will crack up and collapse. If you have watched some of the videos of Antarctica and Greenland, when the glaciers crack up and collapse, they are absolutely nonlinear and dramatic phenomena. No model includes that. Model assumes that ice will slowly melt. That's not the way it occurs. In reality, both Antarctica and Arctic will crack up when the conditions are right. So that is a fear. For example, right now, there's a discussion in COP26 between 1.5 and 2. Why are we debating? Because we don't know at what point further feedbacks, further nonlinearity will come into play. So in modeling, you have to go further, especially for ice sheets and glaciers. Their modeling is still very crude, and one needs more observations in those places to see how ice pieces crack up and fall. Okay, they don't do it in any way. So I think the major part which is unknown right now is the role of ice, and secondly, the second part which is very, very worrying is the permafrost. All of Central Asia contains a large amount of frozen soil. We don't know how methane will come out of that frozen soil as the temperature rises. And if it comes out rapidly, it will add to the radiative forcing that's already happening. Now, that is the fear we have, not today, but 20 years from now, that as the temperature goes beyond 2 to 3 degrees, additional warming will start coming on which we have no control. Remember that we can only control CO2 emission. We cannot control the emission of methane from permafrost. So those are the areas people are concerned about. And of course, monsoons. See, monsoons modeling, we have progressed a lot, but we still don't know whether monsoon has a tipping point, at which point monsoon will shift. We don't know. We think it is not there, but there are papers claiming that monsoon has a bifurcation point. I don't agree with that because they are very simple models. But one cannot rule out that as you take more complex models, especially those in which you're going to resolve clouds. Right now, most models parameterize cloud. They make simple assumption about when clouds will form. Now, in the next 10 years, we are going to get models with a resolution below 1 kilometer, in which the cloud formation will occur at the level of 1 kilometer, which will be closer to the correct physics. When that happens, it may turn out that some of the models will show instabilities which are not seen today. As a matter of fact, there are 1 or 2 papers showing that some of the high clouds may rapidly increase, and that will cause more greenhouse effect. So that's already emerging, but that's not full global model. So there are a number of places where we have to improve further. And remember, Earth is such a complex system, we can never say we have been able to model the entire Earth. We have to be humble and accept that fact that we can only model parts of it. And to me, the real challenge in the future for young people is not making more complex models. That will happen. Is understanding. That's why I gave the quote from Manabe that if you have running a model, very complex model, and it gives you a very strange result, if you don't understand it, it is like astrology.
Yes.
So that's the point, very important point, that a model output which doesn't make sense may actually be garbage. Now, that is where all the effort of young people in the next 30 years will go on. Computers will get faster, they'll get more complex models, but somebody has to sit down and figure it out whether what the model is saying is right or wrong based on our understanding of the system. Although the system is complex, people like Hasselmann and Manabe have been able to interpret the complexity through simple models. That is a must. that goes along with a more complex model. We need a more complex model because ice, glaciers, permafrost, and so many other factors are not well represented. Clouds, for example. Clouds still are very primitive in the models. Okay, is that
all right? Yes.
Okay? Yeah.
Yes, sir.
So,
actually, in continuation with that, when you say the permafrost and the melting of glaciers, like for example, there is also a wide belief that because of the biological life present in these ice sheets, the microbial roles in melting of these ice, would incorporating that data also help us to make our models a little more clear?
yes, definitely. I had another point about these models. Although models include vegetation, they don't include too much biology. Okay, I'll give an example. Only one model in the last 10 years put a bacteria in a climate model. Can you believe that? That bacteria controls clouds.
Yes.
Condensation on the aerosols. So
Yes.
there are many things happening on this earth we don't understand, and hence we don't model. So the biggest fear people have is that right now we are assuming that the photosynthesis is going on in the ocean and forest will go on as before. It may not. Now, until you model those oceanic species which fix carbon dioxide, we don't know what are the possibilities there. So people are warning that at some point beyond a certain level of CO2 and temperature, ocean may not be able to absorb CO2 the way it's absorbing today. If that happens, we are in deep trouble. And that's why people who have some amount of humility, they are warning their leaders that don't let the temperature go beyond 1.5 because we don't know many things about our world. And to assume that you can let it warm to 2 to 3 degrees and somehow it will adjust is based on no data.
Okay.
Okay, are there any other questions? Anybody else? Chandan, can you see anything in the chat box? Anybody else put any chat box by any chance?
No, sir. I couldn't see, can't see any.
Okay, fine.
In the chat. Yeah.
So I think, okay, Vishal has another question. Okay.
Can I ask another question? Yeah.
Sure,
So
sure.
I wanted to hear your comments, Jace, about do you think with this Nobel kind of prize, complexity in physics is recognized as a valid challenge as opposed to the newness of the phenomena?
But let me tell you, already physicists are very smart people. You know that. They had already recognized complexity more than 30 years ago. So the point is, it is that to give a Nobel Prize, the committee has been convinced it has some impact, practical impact. So, so it has come this year. But remember that within the physics community, there's a whole group which is looking at complex systems. May not be Earth climate, but other complex systems. For example, in IISc, Professor Sriram Ramaswamy works on various complex systems. So the physics people have recognized it, but yeah, it's a small community compared to those who work on quantum mechanics and cosmology and so on. But I think until and they come up with stunning results, they won't get Nobel Prize. Nobel Prize, the what do you call, the threshold is very high. It has to be important for society or very important in opening up new fields. So complexity discussion, I remember 30, 40 years ago, it had started. As a matter of fact, Professor T. M. Ramakrishnan, who was in physics department at IISc, quoted Anderson, Nobel laureate, saying there are only 3 important topics in physics. They're very small, they're very large, and they're very complex. Very small is quantum mechanics, very large is cosmology, and very complex is everything else, climate and biology and everything else. So these are 3 domains of physics in which work is going on. But recognition depends on many factors, and also depends on the subjective bias in the Nobel Committee. Remember that also plays a role. So one shouldn't give too much importance to the Nobel Prize. It's a great prize. I think they do very hard work to come up with this one. But remember, every year when they give 1 or 2 prizes to 2 or 3 people, there are at least 100 people who deserve it. That's the quality of work going on in the world. So which 3 get it is purely a lottery. As a matter of fact, if you look up at some websites, they tried to predict who will get Nobel Prize. They never got it right because it's very hard to decide which of the 100 the Nobel Committee will pick. That's purely a lottery. So I think one should not give so much importance to Nobel. That's why I like Manabe. Manabe didn't get overexcited by the Nobel Prize. He is a very humble person. He was surprised that he got it, and he thought he really didn't deserve it. So to me, one must recognize that a lot of creative work is going on in all areas of physics, chemistry, biology, climate, and other areas. And only a small portion can be recognized by the Nobel Committee because there are only 3 prizes relevant to these chemistry, biology, and medicine, chemistry, and physics, and of course peace, which IPCC got. But there is much more creative work going on. But now and then they will come up with something grand, which has either societal impact or impact on the field, then they'll recognize it. So as I told you, they recognize lasers, LED, exoplanets. So